So today's video is on mass spectrometry. So what is mass spectrometry? Well, it is an analytical technique used to study ions. And so mass spectrometry can be used to calculate relative atomic mass, relative molecular mass, relative isotopic mass, and molecular structure. So mass spectrometry is a technique used to study ions. And what is time of flight mass spectrometry? So this is the type of mass spectrometry that we'll be looking at. And it measures the time taken for ions to fly a known distance. And it uses this time to determine their masses. So it's time of flight because it measures the time the ions are flying a known distance. And we'll be investigating this in a minute, so don't worry if you don't really understand it yet. So how does mass spectrometry work? And we are going to be looking into these steps a bit further, but we're just going to set them out now so you can see where it's going. So first is vaporisation. So our sample is turned into a gas. Then ionisation, so our sample is formed into ions. Then acceleration, so changing the velocity, and the sample enters drift, so the particles are flying. Then it's detection, so we're detecting the different ions. And then analysis, so we're turning the information that we found from the detection into a mass spectrum. And a mass spectrum is just this sort of graph up here, so it's displaying the information we found from our detection. So these are the simple steps, but we'll be going into these further now. So vaporisation. So an electrical heater is used to turn the sample into a gas. So we're turning all of our samples, it doesn't matter what it's going to be, we're going to want it in its gaseous state. So we're going to use an electrical heater to do this. And it's important to note that our entire mass spectrometer is going to be in a vacuum. So this means that the air molecules won't be disrupting the sample's movement. So if we're wanting to measure how long it takes for a particle to fly a known distance, we don't want it colliding with air particles being diverted from its track, so extending its time of flight unnecessarily, so we calculate wrong information. We're going to want it complete vacuum so the particles and the ions can fly smoothly and we can get an accurate reading of its time of flight. So vaporisation, electrical heater turns it into a gas. And now ionisation. So our gaseous sample now enters the ionisation chamber, so that's here. And high energy electrons are emitted from an electron gun, and an electron gun is an electron emitter. So you can see here, this is going to be our electron gun, and it's going to be emitting high energy electrons. And these high energy electrons collide with our gas sample. So our gas sample is going to be travelling along this dotted line. So as our gas sample comes through here, it's going to be hit with these high energy electrons. And these electrons that are colliding with our gas sample take another electron from the atom. So as these electrons collide with the sample, it knocks other electrons off, but only one electron per atom. So we can form 1+ positive ions. So you can see here, our gaseous sample is collided with one electron, and this knocks off another electron, so we have our electron that has collided with it and another electron that's been knocked off of our sample, leaving us with a 1+ positive ion. So that's the ionisation. And now we go into acceleration. So our ions are 1+ ions that we have formed from the ionisation chamber. So our 1+ ions are accelerated by an electric field in this acceleration chamber here. And this electric field that we're using to accelerate our ions accelerates all of the ions to the same kinetic energy. So it doesn't matter what mass these ions are, we're going to be accelerating them all to the same kinetic energy. And just to remind you, the equation for kinetic energy is half mass times velocity squared. So our acceleration is accelerating all of our ions to the same kinetic energy, and that's really, really important. So now we're going on to drift. So our accelerated ions enter the drift region. So after our acceleration chamber, our ions enter this drift region here. And because all of our ions have the same kinetic energy due to being accelerated, their mass determines their velocity. So along this drift region, our ions are going to be flying at a certain speed. So they're going to be traveling along here at a certain velocity. And because they all have the same kinetic energy, it is going to be their mass that determines this velocity. So as I said before, kinetic energy is half of the mass times velocity squared. So if we rearrange this to find our velocity, all ions have the same kinetic energy, so it's going to be their mass that determines this velocity. And so our heavier ions will travel down this drift region slower than lighter ones. So our heavier ions will be at a slower velocity than our lighter ions, which will be travelling at a faster speed. So this means that our heavier ions will have a longer time of flight. It will take them longer to travel this distance than lighter ions. So our heavier ions have a longer time of flight, our lighter ions have a slower time of flight. So then detection. So our ions, after travelling down this drift region, flying along this known distance, they will hit the detection plate at the end. And they will hit this detection plate at different times due to their different velocities. So the lighter ions will hit the detection plate first because they're travelling at a faster speed. So the detector produces a varying electric current when hit by the ions based on their abundance. So if a larger number of one type of ion were to hit the detection plate, it would produce a larger electric current. So the more of that type of ion that there is, the larger the electric current. So if there are more heavier ions, then a larger electric current will be produced when this larger number of heavy ions hit the detection plate than a smaller number of lighter ions. So if our light ions have a smaller number, a smaller abundance, it will produce a smaller electric current. And this computer system uses this to calculate both mass of the ions and their relative abundance or intensity. So now analysis. So our computer system uses this information to generate a mass spectrum. And as I said before, a mass spectrum is a graph displaying the information that the detector found out from our mass spectrometry. So on our y-axis is relative abundance, and this is usually percentage relative abundance. So it would usually be out of 100. And we attain the relative abundance based on the size of the electric current. So if the electric current produced by a certain ion is larger, we know it's going to have a larger relative abundance. So then we have our mass to charge ratio on our x-axis. So all of our charges of our ions are +1, so we have +1 ions. And so our mass to charge ratio is really just mass, because if it is the mass of the ions over 1, over our 1 plus charge. So we can take the x-axis as just being mass. And our mass is determined by its time of flight, so the time taken for our ions to travel in the drift region. And this is because the mass determines the velocity, so its speed is determined by the mass, so we know that the time of flight, the time it takes to travel that drift region, is proportional to the mass. So then lastly, we're just going to look at calculating relative atomic mass. And relative atomic mass is just the average mass of all of the isotopes. And so we can say that our relative atomic mass, calculated from our mass spectrum, would be the percentage relative isotopic abundance times its isotopic mass plus the percentage relative isotopic abundance times the isotopic mass of the other isotopes, and so on. So this would be one isotope, that would be another isotope, and it would continue for as many isotopes as your mass spectrometry detected. And then that is all over the sum of all of the relative isotopic masses. So usually this is 100, but it can catch you out if all of the relative abundances add up to more than 100 or less than 100. So just be careful about that. And our relative isotopic abundance that we see here is just the y-axis abundance. And our isotopic mass is just our x-axis, our mass over charge, because our charge is just 1. So basically this is going to be the y value times the x value plus the y value times the x value of the different isotopes along our mass spectrum.